Okay, today I thought we'd look at another problem. We're kind of generalizing a bit now. Launching a projectile from a cliff or some height h. And so we're not dealing with level ground anymore. And I want to look at a couple things about this, like what's the range, what's the maximum range, what the total flight time is, etc. But I want to look at these from a couple different perspectives. I'll start with basic kinematics, but it'll turn out that that's really nasty. It's doable, but I'm going to skip a lot of steps because there are better ways of doing this. So let's start with the way that you'd probably approach this if you saw this in a physics class. You'd say, okay, let's say I want to calculate the range. Where will this land for a given launch speed and a given launch angle and a given launch height? So let's go ahead and use our constant acceleration kinematics equations. And notice that our final height will be 0, so I'll use my standard coordinates setting this to be my origin. My initial height is h. My initial y velocity will be v naught sine theta. The time it takes to get from here to here, we usually call that the flight time. I'll call it capital T. And then the acceleration in the vertical direction is negative g. Now, this is a quadratic equation for t. Unlike previous cases where everything was level ground, I could factor out a t. Now I can't. I actually do have to use the quadratic formula. So we'll just do that real quick. T equals. Now, we're going to see that although you might think there's a plus or a minus, we're only going to take the positive root because we want our time to be positive. So I'll have negative b plus or minus root b squared minus 4ac, that's 4 times negative 1/2 g times h, all over 2a, which will be negative g. Now we can see that the negatives here will cancel in all three terms. Since the term inside the square root is bigger than the term outside, I really do need these to have the same sign because otherwise I'd get a negative value for my time. So let's quickly do that. So the negatives all cancel. I'll go ahead also and pull out some stuff. So there'll be a v naught over g. There'll be a sine theta plus. And now when I pull this out, notice that the 2 and the 4 partially cancel. These both become pluses. When I pull this out, I'll have a 2gh over v naught squared. Okay, let's write that. So we'll have a sine squared plus 2gh over v naught squared, because I'm imagining pulling out a v naught from all of these. And just to make life a little bit simpler, because this is going to come up quite a bit, let's go ahead and define a symbol for this quantity. I'll call it beta. 2gh over v naught squared is dimensionless, and it's just going to be some constant that depends on the initial parameters of the problem. All right, so my final result then is v naught over g sine theta plus root sine squared plus beta. And that's it. It doesn't really simplify any more than that. So that's the total time in flight. I can then go to my x-coordinate kinematics equation. It's going to land at x equals r, starts at x equals 0. I do have a v naught cosine theta this time, and I'll multiply it by t, but there is no acceleration in the x direction. So I end up with this range. V naught times this will just be v naught squared over g sine theta plus the square root of, that should have been a theta there, sine squared theta plus beta. Okay, and then we also need to put our cosine theta on here as well. Now, if I go back and look at the case when h equals 0, then beta equals 0, I get sine squared, square rooted is sine, plus another sine is 2 sine. 2 sine cosine gives me sine 2 theta. So we recover the old formula in that case as well. But now, let's say that I want to go to the next step and say, what is the maximum range? Or rather, what theta maximizes the range for a given launch speed. If you want to do this, you would have to set 0 equal to the theta derivative of r. And that is going to be gnarly. Now, while you can do that, take the derivative. You will need product rules, quotient rules. Well, not quotient rules, but chain rules. It'll be very nasty. This is a mess. So let's see if we can do it a different way. We got our formula. That's not too bad, but the derivative is going to be a little too nasty. So let's see if we can do this a different way using, say, just geometry. Okay, so on the board, I've drawn a couple vectors. Here we have v naught. This is the initial velocity vector when it's launched. I also drew in v. This is the velocity vector right before it hits the ground at that maximal range point, or at the range in general. And notice that because we know that the vector equation v equals v naught minus gt, let's call it j hat or something for the negative y direction, is the vector equation that describes the velocity as a function of time. And this is purely in the vertical direction. G times t is the deflection. It's the amount the velocity has picked up in the y direction by virtue of the acceleration due to gravity. So because that's vertical, we end up with a nice triangle here where I know that this side is vertical. I know this part of the launch angle is theta. Vx is the initial, maybe I should call that, it doesn't matter if you call it Vx or Vx naught because there's no acceleration horizontally. And we know that if I want to calculate the range is supposed to be Vx times t. After all, that is the range of this projectile as a function of time. Now, let's notice something here, that if I want to calculate the area of this triangle, and this triangle is not a physical triangle, it's not really in space, it's made up of velocities, but let's imagine I want to calculate the area of this triangle. I'd use my good old-fashioned 1/2 base times height, so 1/2. The base of the triangle, I'm going to call this vertical piece gt, and the height, this is a perpendicular right here, is Vx. But look, Vx times t is exactly r, and g and 1/2 are constants. That means maximizing the range of this projectile motion is equivalent to maximizing the area of this triangle. So if I can maximize the area of this triangle, I will maximize the range. Pretty cute, huh? Okay. Is there another way I can write down the area of this triangle? So yes, I know I can calculate the area of this triangle by using the sine formula. Let's label, say, this whole angle as, say, phi. That's the angle between my initial velocity vector and my final velocity vector. In that case, the area of my triangle can be written as 1/2 the product of the two sides, which will be v naught, times the sine of the angle between them, which is phi. Now, v and v naught are mostly fixed. If you're unconvinced by that, notice that v squared is v naught squared plus 2gh. Or put another way, it's v naught squared times 1 plus beta. And all of those are givens in this problem, that doesn't depend on angle. So v is fixed, v naught is fixed. I want to maximize this area, which will maximize the range. What value of phi maximizes sine? 90 degrees. So I get maxima when phi is 90 degrees. In other words, when my initial velocity vector and final velocity vector are at right angles to each other, or put another way, if I kind of extend this line up here and extend this line back here, that should be a 90-degree angle. In that case, we maximize the range. Okay, how can I use some trig to figure out how that relates to the maximum range? Okay, so using some similar triangles here, once I know that this is actually a right angle, that means that this angle is also theta. So if we use some trig here, I can write down that sine theta, using this smaller angle here, will be opposite, that's V naught, over adjacent, over hypotenuse. Now this hypotenuse GT is also given by the Pythagorean theorem, square root of V naught squared plus V squared. But look, we know what V naught squared plus V squared is by our previous result. And so substituting that in, I will end up with V naught over square root of V naught squared plus V naught squared times 1 plus beta. And canceling out all of the V naughts gives me 1 over root 2 plus beta. That is my launch angle. Okay, so not only have we found a formula for the range using kinematics, we've now maximized that range by finding the launch angle that maximizes this. It depends on beta, which is that root g, let me write that up here. This is a reminder, beta is 2gh over v naught squared. So it's related basically to the height of this launch point. Notice that if beta equals 0, I get theta equals 45 degrees, which we already knew maximized the range on flat ground. Since beta is greater than 0 here, my angle to maximize range is going to be less than 45 degrees, get a little more range going horizontally. This also means that I can go plug this back into, well, the formula we derived with kinematics if you really want. Notice, that was pretty messy. It had cosines and sines. You'll have to do some trig. Or we can go plug it back in here, because I know that R is just going to be given by this formula. So let's bring that up to the top and summarize our results. Okay, so here's our condition on theta that maximizes the range. Maybe I'll call it theta star or something to indicate we're talking about a maximal version of theta. Here's our formula for the area of this triangle. We just said it's maximized when sine phi equals 1, in other words, when it's a 90-degree angle. And if we use that, we can immediately write down that R is going to be V naught over G. But we know what V is from conservation of energy. And if we're going to rewrite this in terms of beta, let's factor out a V naught squared, and we'll end up with V naught squared root 1 plus beta. And sure enough, that makes sense. Notice again, if beta equals 0, I get that maximal range formula on level ground that we'd already calculated. Okay, so we have our maximal range. We could also calculate, for example, the max height and the max, the time this is in the air. But let's turn to our third option. I want to rederive this one last way using a cross product of vectors that might be even faster than this geometric method. Okay, for the final method, let's note that the final velocity vector is the initial velocity vector plus the acceleration vector times the flight time. This is just a vector equation. Also note that the position vector of my particle at this final location is 1/2 the velocity vector final plus the velocity vector initial times t. And we're assuming that I'm now choosing my origin to be here, although it doesn't really matter since we're dealing with vectors and not their components. I now want to look at the cross product G cross R. Might seem like a strange thing to try to cross, but let's do it and see what we get. Solving this first equation for G, I end up with V minus V naught vectors over T. And then my R will have V plus V naught as vectors times T. So notice a few things are kind of nice here. The T's cancel. And now I've got a cross product of two velocity vectors. I have to FOIL this out. But remember, the cross product of the same vector with itself is 0. So V cross V will be 0. V cross V naught will be something. Negative V naught cross V will be that same thing when we flip it. Maybe I'll write that out. V cross V naught minus V naught cross V. Notice V naught cross V naught will give me 0. And since the cross product is anti-commutative, if I flip that around, I pick up a positive sign. The 2 cancels the front 2, so I get V cross V naught. It's kind of interesting that this cross product is equal to this cross product. Let's take the magnitude of both sides. So the magnitude of these vectors crossed together will be the product of the 2. So G times the magnitude of R. I'm going to call that distance here D. This is my vector R that's pointing down to my final location. And so the magnitude of that will just be the length of that vector. We'll call it D. And I need the angle between G and R. Well, notice G points straight down. It's the acceleration due to gravity. And R points along that diagonal D. So that angle alpha that I've labeled here will be the angle between these. And cross products have a sine of that angle when you take their magnitude. On the other side of the equation, well, I'll get V times V naught. Those are the two magnitudes. And then I need the sine of the angle between them. Now, I crappily back extended these two rays, so we know the angle where they cross. It's the same angle that I called phi in the previous version. That's this angle up here where these two lines of action or these two rays cross. All right, now again, I am trying to maximize the range. And notice that we can rewrite this range, R, in terms of alpha and A from geometry. R is going to be what? Let's see, I want D sine alpha. So this is G, or said another way, D is equal to R divided by sine alpha. The sine alphas cancel. I guess I could have gone straight to the D sine alpha equals R. But the point is that R is just V naught over G times the sine of this angle phi. That's actually the result we got on the previous board. And once again, V is fixed. Remember that conservation of energy still holds here. V squared is V naught squared plus 2GH. Or if you want, V is equal to V naught root 1 plus beta. Plugging that in here and then saying, what's the question? How do we maximize the range? It's still the same question about maximizing sine phi. In other words, its maximum is when phi equals 90, which gives us back the same result that we had earlier, that the maximal range, I'll call it R star, is going to be V naught squared over G root 1 plus beta. And again, I want to stress how much faster this method is than trying to take the derivative of that horrible range formula that was written in terms of theta directly, setting that to 0. There'll be a bunch of trig, all to get this final result. And don't forget, we also had the result that the angle itself could be found, that was a 2 actually, generically, and then this is the maximal range angle. So we've done it. We have found our max range for a projectile launched from a cliff in 3 different ways. The last 2 were similar, but both of them were infinitely better than trying to do this kinematically with calculus and all the messy trig that comes along with it. So there we have it, and we'll kind of continue with this idea in future videos. QED.